Good afternoon and welcome back to our AP Physics 1 review sessions. I think we're up to episode 30, something like that. So thank you for joining us once again. Those of you that have been watching throughout, we appreciate having you. Those of you that have joined sporadically, we also appreciate that. And those of you that are just tuning in this week for the practice exams, we welcome you as well. If you are just tuning in this week, keep in mind that we have a lot of videos focused on content review, and Greg and I went over that content review kind of with this exam in mind. So it's not just the topics, but it's really how those topics can be applied to this particular year's exam format. So if you haven't checked out some of those past review videos, those are still available for you. So feel free to check them out as needed. My name is Joshua Beck. I'm coming to you from Clayton, North Carolina. And yesterday we went over the kind of the College Board demo site for how to navigate the whole exam experience. We talked about some of the logistics. I've been getting a lot of useful or very great questions on Twitter about this process, and I'm doing my best to help answer those. But please keep in mind that any answers that we give you about this testing format is based on what we've looked at, things like that. Please don't take what we say as absolute gospel. Please make sure you're actually checking out the College Board links and reading all the fine print yourself, and make sure that you are staying accountable for what they've actually published with all the specifics. But generally speaking, I would say at this point, you should have a pretty good idea of which submission technique you would like to use. And all of your practice from now until the test day, you should really try and practice in that format. So if you are planning to type, then I would really suggest trying all your practice problems by typing moving forward. If you're planning to upload photos, then make sure you are practicing this process of taking pictures of all your work and making sure it's formatted properly. Make sure you get in the habit of putting an ID number on the top, things like that. So make sure whichever technique you're going to use, make sure that you're utilizing that during your practice moving forward. So that on exam day, you have gone through the logistics multiple times and that part feels completely normal. So that way the physics is the only part that you're really being assessed on. So make sure you give yourself ample time to practice the actual logistics. Now, today, what I want to do is just simply go over the questions from yesterday. I started with a short warm-up yesterday that we followed through within the template. Some of you may have recognized this problem. You may have seen something similar to it. Hopefully you recognize that there were a couple minor differences with what I actually asked. So let's go ahead and jump into part A. It says here, part A of this question is originally formatted asking you to determine if these carts, after they collide, if they'll remain at rest, move to the left, or move to the right. Now, I asked you to briefly explain how you would use that information to find your answer. So what I actually want to do is go through the actual process of finding the answer. I'm going to go pretty quickly. For cart A, it has some gravitational potential energy that turns into kinetic energy, and I've substituted in the M and H values that were given. That tells me that when it reaches the bottom of that ramp, this is going to be the speed of cart A. If I go through the same process with cart B, plugging in the values that I got for its mass and its height, I end up finding that this will be cart B's speed. Now, if I compare these two, I can tell that the cart on the left and the cart on the right, so cart A and B, have two different speeds. So you may think that the speed is what's going to be important in determining the final direction once they collide, but it's not. Remember that during a collision, if we have a closed and isolated system, so if we have no external forces, and if the mass isn't changing, then we know that momentum has to be conserved. Now, momentum will not be conserved while it's on those inclines because we've got this external net force. Okay, or we have this unbalanced force rather. Once it's on the flat part though, then we don't have any unbalanced forces left, so momentum is going to be conserved from that point forward. So what we could do is set up the momentum of the system, momentum of cart A and cart B, once they're on the flat part. We already found the velocity of cart A, so I'm going to just take MA times VA that I just solved for on the previous page. I'm going to compare that to MBVB. That'd be the mass of the second cart and its velocity. Now this is going to the left, so I have the opposite sign on this to indicate the opposite direction for this momentum vector. Now I'm going to go ahead and pull this square root of 4. I'm going to go ahead and pull that out as 2 so that I can see this a little bit more clearly. Now at this point, I can see that the momentum of these two carts, the magnitude of these momentums are different. So the cart that's on the right, cart B, will actually have a larger amount of momentum, just the magnitude will be larger than cart A. So that means the system as a whole will have a net momentum that's to the left before the collision. So it has to have a net momentum to the left after the collision. Now you're probably wondering, why am I going through all these calculations? It didn't ask me to calculate. Or you might be thinking, how in the world am I supposed to upload this? You were telling me to copy and paste my work, type it in a Word document. How am I supposed to do all this in a Word document? Well, let's go back to the actual question I asked. I didn't actually ask you to do this. I asked you to describe how you would use that information. So I'm asking you to describe what I just showed you. Now that was the way to come to the actual mathematical solution, but let's just describe that process. This is what the question truly asked. 1, I'm going to use conservation of energy to find the speed of each cart. That's what I just showed you. Again, the problem I gave you yesterday didn't ask you to do that. It asked you how you would get to the answer. After I found the speed, I would use that speed and the given mass to find the momentum of each cart. I couldn't start here because the problem didn't give me information about the speed. It says, how would I use the information above? The information above gives me the location and the mass of these objects. So I have to use conservation of energy to find the speed. Then I can use that speed with the given masses to find the momentum. And then the direction of the cart with the larger magnitude of momentum will be the direction of the cart after the collision due to the conservation of momentum. So here in these 3 sentences, I've described how I would use that information. The previous slides, if you're curious, that's the actual mathematical process, but that isn't what you were asked to do on this particular problem. I asked you to describe or explain how you would use the information. So here's how I would use it. Now for part B, consider the time interval from when the 2 carts are released until just before they collide. Okay, so not after the collision in this particular case. What I've asked is just before they collide. So this is really a question about defining your system and then identifying which forces come from within your system and which forces come from outside of your system. So in the first one, the Earth cart system. So we've got both carts and the Earth are all part of the system. The system will have potential energy because these carts have been displaced from where they would naturally want to be, which is close to that surface of the Earth. So they've been displaced, so there's going to be some potential energy stored in this cart-Earth system. That potential energy will be converted into kinetic energy. The force that's doing that is the force of gravity, but because Earth is part of our system, that force of gravity is an internal force. So it's capable of converting energy from one form to another, but it's still the same total amount. In the cart system, now the Earth is no longer part of my system. So now I have these 2 carts, they don't have any energy at the top. There's no potential energy here because the Earth is not part of our system. So they haven't been displaced from anywhere because the Earth is not part of our system. So they have no energy at the top. Then as they work their way down the ramps, work is actually going to be done by the force of gravity, which this time is outside of my system. This is an external force. So that work is going to add energy to the cart system. That'll account for our increase in kinetic energy. Now, could you approach the problem one way? Yes. Could you approach the problem the other way? Absolutely. And both of these analyses would give you the same kinetic energy if done properly. Okay, but it's important to define your system so you can then identify which forces are internal. Those forces just convert energy from one form to another, and you identify which forces are external. And if you have external forces, those are capable of doing work, so changing the total energy of your system. All right, if you have any questions about that, please feel free to reach out to me. I wanted to put that in there just as a quick little refresher about defining your system and how things behave once you've done that. All right, next up, moving right along, we got to our full-length problem. You'll notice that this full-length problem was definitely longer than other released FRQs. Keep in mind that the exam format this year is different. Yes, we have a paragraph style question, okay, or a question requiring this paragraph length response, just like we have in the past, but it's going to be a little bit longer question as a whole. We have QQTs, just like we've had in the past, but these questions will be a little bit longer than they have been in the past. If you look at past released free response questions, you can see the estimated time to work listed on each of those questions. Well, here you also have the estimated time for these questions, and you can see that the time estimate's a little bit longer. That's because there's a little bit more information in the question. So let's dive right into it. Here we've got a sphere moving around on a string like this. All right, student 1 says that none of these forces exerted on the sphere are in the direction of point C, which is the center of the circular path. Therefore, I don't see how there can be a centripetal force. So there's a couple possible misconceptions. Student 1 is falling into a couple of these areas, which would be considered misconceptions. A lot of students think that centripetal force is a separate force, and we talked about this a few weeks ago. Centripetal force is not a separate additional force. The centripetal force is created from sort of your usual suspects. It's going to be some combination of T, normal force, frictional force. It could be force of gravity might play a role, right? A centripetal force is going to come from your usual suspects. It's not an additional new. Another misconception students come up with is that FC must be just a single force. There has to be one force that's aimed at the center, and that force will be my centripetal force. Sometimes that's the case. Sometimes there is one force that's directed towards the center, and that's it. Other times it's a combination of multiple forces, right? A couple weeks ago, I was spinning the bucket, and when the bucket of water was above my head, it was a normal force and the force of gravity working together to create the centripetal force. So it doesn't have to be a single force. And then another misconception here that this student is probably falling into is the idea that the entire force must be towards the center if it's going to create a centripetal force. And we need to remember that even a component of a force can be directed towards the center. If part of that force is towards the center, then that can create centripetal acceleration and thus create circular motion. So let's take a look here. We are supposed to identify one aspect of student one's reasoning that's incorrect. So I'm going to start this by saying student one incorrectly reasons. I like to start with something like that. If I'm trying to explain what is incorrect about somebody's statement, I like to explicitly say student one incorrectly stated or reasoned and then go on with it. If I didn't put that in there, sometimes it can be confusing. Am I starting to add my own explanation? Am I starting to explain why that's incorrect? So what I want to do is first I want to answer the question that says, what is one aspect? So I'm going to identify the aspect that I'm addressing. I'm going to say student one incorrectly reasons that FC must come from one separate force in its entirety. Therefore, this object cannot travel in a circle. Now I'm going to explain why that's incorrect in this case. Is there a force pointing to the center? Well, not an individual force. mg is not pointing towards the center. T is not entirely aimed towards the center, but part of it absolutely is. So why was student one's statement incorrect? Well, because the horizontal component of T is towards the center, and that can create centripetal acceleration and thus circular motion. So again, I've tried to explicitly indicate which incorrect reasoning am I addressing, and then why is that incorrect. Now student two decides to chime in, says, hey, you know what? I see another problem. The tension force exerted by the string is at an angle from the vertical. That's true. Therefore, its vertical component must be less than the weight of the sphere. That means the net force on the sphere has a downward vertical component, and the sphere should move downward as well as moving around in a circle. Now I'm going to address this issue of talking about movement in just a second, but first let's answer the question. What is one aspect of student two's reasoning that's incorrect? Well, again, I'm going to explicitly mark out, hey, I'm going to identify what they said that's incorrect. That way there's no confusion whether or not I'm starting to explain myself or correct it. I want to be really clear. Student two incorrectly reasons that the vertical component of T is less than mg. And now I'm going to explain why that's not the case. See, the problem states that the sphere moves on a horizontal circle. The problem tells us that. So what's wrong with student two's reasoning? Well, in order to move on this horizontal plane, the vertical forces must be balanced. So the vertical component of T must equal mg. Student two said that the vertical component was less than mg. Well, that would create a downward acceleration. If we had any sort of acceleration on the vertical, then this object would not be staying on this plane. So in order to stay on this horizontal plane, we need our vertical forces to be balanced. So we need that vertical component to equal. So what I've done is I've explicitly said what was incorrect about student two's reasoning, and then I've explained why it was incorrect. Now, a quick little side note, not necessarily relevant in this particular problem, but this student is explaining the movement of these things, saying downward motion, move upward, move downward. So just a quick little side note, just in general, as you move forward, please don't confuse movement, which is describing the direction of a velocity, and acceleration. Okay, if we're talking about movement, a lot of times students use these words interchangeably. They talk about movement when they're trying to talk about acceleration or net force. Movement describes the direction of our velocity. Okay, now the direction of our velocity could be affected by an acceleration, but the direction of the velocity is not always in the same direction as an acceleration. Okay, so you should just be able to picture a few scenarios where you have a velocity, but acceleration 0. You should be able to identify scenarios where the velocity might be 0, but acceleration is not, right? You should be able to identify scenarios where v is in one direction, but a is in the opposite direction. And then obviously scenarios where they're both in the same direction. So just a side note, be careful with your words. Don't confuse movement with acceleration or net force, okay? So let's move on to the next part. This next part probably threw some people for a loop. You're not expecting this. Whoa, why are there all these equations here? Well, keep in mind, in acute QT, we're going to try and look at a scenario analyzed with our physics principles, and then we're going to try and look at it with some sort of a derivation or some sort of a derived equation. Sometimes these equations that are given to you will be correct. And in this case, they tell you that these equations are derived correctly. Sometimes they'll give you an equation and they won't tell you if it's correct or not. And they'll say regardless of whether or not it's correct. And we'll see that a little bit later in the problem. But here we're told these equations are correct. So I can use these equations to try and see if I can challenge student one's claim. Now I'm just going to reiterate. Student one claimed that none of the forces exerted on the sphere are in the direction of point C. So there's no centripetal force. So I'm going to use this first equation here. And this first equation shows us that as long as there's any radius, so if it's moving in a circular path, as long as there's some radius, then there is a net force. And that net force will be the horizontal component of T. So that horizontal component of T is going to be T times the sine of theta. Sine being the opposite over being R over L. So this first equation shows us that as long as there's a radius, then there is and that net what's creating our centripetal acceleration. All right, student 2, I see another problem, right? Its vertical component must be less than the weight. So I'm going to use the other equation in this particular case. And I'm going to start with a little preliminary analysis here. The vertical component of T, right? This student is having issue with the vertical component being less than mg. So the vertical component here, just to show you the geometry, is going to be T times the cosine theta. Cosine would be adjacent over hypotenuse. So that would be H, what I've defined as H over L. But H is a side of our right triangle. So if I use a squared plus b squared equals c squared, I can see that H is actually going to be the square root of L squared minus R squared. You can see that work up above. So basically, what this equation is showing me is this equation actually shows me that the vertical component of T, that's the entire part on the right, that's the vertical component of T, shows me that that vertical component is not less than mg. Student 2 said that the vertical component would be less. This equation shows me that it's not less than mg, it's equal to mg. All right, let's move on to the next part. Here we're given equation. Here, regardless this equation is correct or incorrect. These students are observing the relationship between R and speed. Okay, so it says that this is the equation that they came up with. It says regardless of whether this equation is correct or incorrect, does it plausibly model the student's observation? Okay, so the students observed that as R increased, the speed would increase. Let's see. Yes, that equation absolutely supports that. Now, we're not asking whether the equation is correct or not. We're just asking, would this equation support this? And the answer is yes, because v, or speed, is in the numerator. So if v is increased, then r will increase as well. This is while L and G are constant. So keeping the same length string and keeping it in the same gravitational field, then the only other variables here would be v and r. And so if you increase v, then r should increase as well, which supports their observation. Now, does that mean that their equation is correct? Not necessarily, but it does mean that their equation does in fact support their observation. Until we get to part F. Why doesn't the equation correctly model this relationship if v is very fast? Well, we just said, what happens to r if v keeps increasing? Well, as v continues to increase, r would increase as well. Okay, that sounds fine. Okay, so let's increase V a little bit more. What does R have to do? Increases some more, right? Okay, let's keep increasing V, keep increasing V. Well, then R is going to have to get bigger and bigger and bigger. But eventually, remember, there's physical constraints here. Eventually, R would have to become greater than L, and that's not possible. Why isn't that possible? Well, because the string only has a length of L. So even if we were to spin it all the way out here, the largest radius we could possibly get would be a radius of L. So something's not right with this equation. You don't have to determine what that is. You just have to identify why does this equation not correctly model it if V becomes very fast. All right, next part of our problem, I've retyped this so the format looks a little different, but the next part of the problem is that instead of moving on a horizontal circle, we put it on a vertical plane. We basically turn it into a simple pendulum. We keep theta max relatively small. That way our period of a pendulum equation is going to be valid. And then we create this graph. We change the lengths and we graph the square of the period. Now, I want to briefly show you why we're graphing the square of the period. All right, this is the equation for the period of a pendulum. See, t is not directly proportional to L, so if I were just to graph t versus L, I wouldn't have a straight line. But if I square everything, I get t squared equals 4 pi squared over g times L, and we can see that t squared is directly proportional to L. So if I put t squared on my y-axis, L on my x-axis, I will get a linear relationship. I get this straight line, and the slope would be this m term. That's going to be 4 pi squared over g. Now, this question didn't ask you to do any of this. I'm just showing you why we've graphed t squared versus L. Are there other things you could graph to get a linear relationship? Sure, but we don't need to go down that road. We have a perfectly acceptable linear relationship graphed right here. So let's look at the actual question. Explain how the above graph would change if the mass of the sphere is increased. Well, the graph would not change because m does not affect t. That's it. The period of this pendulum is not going to be affected by mass. Will mass change the size of the forces that are at play? Absolutely. Will it change the total amount of energy we might be dealing with as this thing moves through its range of motion? But none of those are going to affect the period. Okay, you can certainly go back to the simple harmonic motion lesson from a few weeks ago. I definitely covered this in detail, so feel free to go back and take a look at this. Next part says, well, what if the maximum angle is decreased? What if the maximum angle is decreased? Okay. Well, the graph will not change. See, we already said the maximum angle is relatively small, so we've got this approximation for the period. So if we've decreased our maximum angle, then it's still relatively small. And so as long as our angle is small, then it's not going to affect the period. You can look at your equation for the period of a pendulum, and theta is not part of it as long as you're at these small angles where this equation is valid. Finally, how would this change if the pendulum is taken to the moon? Well, what do we know about the moon? Right, the moon is going to have a weaker gravitational field. So the gravitational field, g, which would be equivalent to the acceleration due to gravity for an object in free fall, that g value is going to be smaller on the moon. Now, you may know exactly how much smaller, you may know what factor it is. That's not important. You just have to recognize that it's smaller. So in this case, the graph will become steeper. That's what's going to change about the graph. It'll become steeper because decreasing g will increase the period for any given L value. I'll give you an example. Even if we just cut g in half, so even if it was g over 2, and going from Earth to the moon is a bigger change than that. But even if we were to just cut g in half, that would double all these t squared values. So that one would be there, that one would be there, that one would be way up there, and we'd end up with a line that looked more like this. We definitely have a steeper line. See, remember this term right there was the slope of my graph, and you can see the slope is inversely proportional to g. So if I'm going to decrease g, then I'm going to get a larger slope. All right, on to the next part of the problem. This graph shows the angle theta from the vertical. So we're measuring that angular displacement from here and then there, calling one of these the positive side, one of these the negative side. We can see it oscillates back and forth. Now this question asks you to explain two different things. It says to explain how the graph shows evidence of a net force and and how it shows force is a restoring force. So be careful when you're reading this problem. It asks you to explain one thing that I've put in bold so we can see it, and something else. So we need to explain two different things. So let's start with the first part. This is a position versus time graph, right? We're graphing the angular position. Well, on a position time graph, the slope tells us about the velocity. So a changing slope, the slope of this graph is changing, right? Sometimes it's 0, sometimes it's positive, sometimes it's negative. That slope of my graph is changing, so that indicates a changing velocity. Well, if my velocity is changing, that means that there's an acceleration. And if there's an acceleration, then there has to be a net force. Not just forces, but a net force, right? So evidence for a net force is visible in this graph because my slope changes, which means my speed changes. And if that speed or velocity is changing, then that means there's an acceleration. And the only time we have an acceleration is if there's a net force. So that's great evidence for a net force. Now, a lot of you may have missed the second part of this. It says, and explain how it shows that this net force is a restoring force. Well, what is a restoring force? Well, a restoring force is some force that's always going to push something back to its original location. So if it gets displaced to the right, it's a force that pushes to the left until it gets back. Now, at that point, it will probably overshoot. So now it's off to the left, and now there needs to be a force that pushes it to the right until it gets back. And then once it's off to the right, there's a force to the left that pushes until it gets back. It's a force that's always trying to restore this to its equilibrium position. When an object is in simple harmonic motion, by definition, there needs to be a restoring force. So some of you may have explained it that way. You may have said a pendulum exhibits simple harmonic motion, and simple harmonic motion requires a restoring force. You could look at this graph and say it oscillates from one side to the other, which demonstrates simple harmonic motion, which requires a restoring force. I'm taking some characteristics from this graph, and I'm going to say that when the pendulum goes past 0, right, we're graphing position, so when that's past a 0 point, it begins to slow down. V will approach 0. See right here, I've got a negative velocity, and then some short time later, I have a velocity of 0. Ooh, so that means once it went past 0, it tried to slow this thing down. Then it sped it up and it gave it this positive velocity until it got back to 0. But once it goes past 0 again, right? So once it goes past 0, it begins to slow down and it will approach a velocity of 0 again. So what that tells me is once it's overshot that equilibrium position, it's trying to slow down. The only thing slowing it down would be this net force, creating this opposite acceleration to slow it down. That net force must oppose the direction of motion, which means that it is a restoring force. And we can see it on both sides. When you end up below this, the restoring force will slow it down. You'll reach a speed of 0, and then it'll bring it back. When it's above, same thing. It slows it down until it reaches 0, and then it brings it back. Make sure you've answered both questions here. Finally, this bottom piece. As the sphere swings back and forth, it must also rotate a small amount during each swing. Okay, so we could look at this problem from two different perspectives. We could look at this problem as the pendulum as an entire object fixed up here, right? And it rotates back and forth like this. Or we could look at that attachment point right here, and then the sphere is beneath it. Okay, and as that point moves back and forth, imagine you were just focused on that view right there. You would see this pendulum bob, this little piece at the bottom, you'd see it over here, and then in the middle, it'd be directly below it. And then when you're on the other side, it would be over here, then it would be directly below it, then it would be over here. Now, if you zoom out, bigger picture, yes, that whole string is also moving along with it. But this question is asking from the perspective when you zoom in and you just see the sphere, you're going to see it here, then you'll see it there, then you'll see it there, then you'll see it here, and then here, and then here, and then here, and then here. Again, if we zoom out from another point of reference, it's rotating like this. But if we zoom in and we just track that connection point, right, then we're going to see the bob over here, and then the bob here, and the bob here. So that's what this question is asking about. It says, with respect to the point of attachment. Okay, so let's look. I've just marked the point of attachment here. Let's draw and label the forces. I've got a tension that's being applied directly at that point of attachment. The tension is not being applied in the center of this. The tension is being applied to the outside of that sphere. It's at the edge. It's at this dot. It's at that point of attachment. mg is the force of gravity on the sphere, and that's going to be directly through the center of mass. Well, if you look closely, it's not much. It's not much. But if you look, there's that slight r value. So the point of attachment, and then we've got this force applied a slight distance away. So that force is going to create a clockwise torque. It's going to be created due to mg being applied at a slight distance r to the right of the point of attachment. So there's the answer to part K. If you have any questions about any of these parts, whether it be the warm-up, or if it's about any of this full-length QQT, please feel free to reach out to me. If you have not tried the demo yet, please make sure that you check out the links here. It's the second one, it's the AP demo website. Please check that out. This is the one that I utilized yesterday. When you log into that, you're not logging in your real information. A lot of people have been asking, well, how do I get my student ID? Remember, you're not using your actual student ID yet. You'll get that with your exam ticket in an email a couple days before the exam. So this demo site, you can just make up a number, just log yourself in, make up the information, put in whatever birthday you want. This time on the real test day, you got to put in your real info, and there'll be more of it. So make sure you log in 30 minutes before, not like 5 minutes before like the demo does. Make sure you log in 30 minutes before your scheduled time, enter all that info. But if you're on the demo site, there's not a real question there. Some people were confused. Why am I not seeing the question here? This is just for the logistics. This is for you to practice your upload technique. At this point, as you get closer and closer to the exam, I want you to start doing all of your practice work on the device that you intend to use for the exam, right? That way you can troubleshoot. Some people yesterday reached out to me, oh, I couldn't get the copy paste to work. And then they switched to a different browser and it worked. Well, great. Well, now that person knows I better use that browser on exam day, right? Or people were uploading pictures and they say, well, I forgot to upload my extra pictures and I realized afterwards that I only uploaded picture 1, even though there were 2 pictures on here. Well, good thing you made that mistake on the demo, because if you make that mistake on exam day, you can't go back. So make sure to use this demo site. Make sure to practice the technique, not just for the sake of going through it and checking it off your list of to-dos, but actually making sure you understand how your device combination will work so that you are prepared to submit without any hiccups. That way you can just focus on the physics on test day. Okay, there's some other websites here, 5 steps to take before exam day, some things how to prep for the exam, suggested documents to have, an exam day checklist. Please take some time. I know the exam is going to be still a little ways off. You still got several days, but that time's going to go by pretty quickly, especially once you get to the weekend. So make sure you're kind of checking off some of these logistics things as you go. Now, tomorrow, Greg has a cool lesson plan for you. He is actually running a full-length practice exam. So when you log in tomorrow, you should expect to see 2 full-length questions. He's going to administer 1 in the designated time frame. He'll give you the upload window to practice uploading it, which if you want to use the demo site to do that, feel free to do so. And then he's going to give you a second one immediately following, because on exam day, once that timer hits 0 for the submission, you got to be ready to go, because your new question is going to be up and ready and your timer is going to start. Remember, you don't get to decide when to start your timer. Everyone's timers start at the same time all around the globe. So make sure you're ready to go. So Greg will give you the first question. He'll transition you directly into the second question, so you can give yourself kind of that full time crunch feeling, so you can see exactly what that's going to feel like. And then on Thursday, Greg will go over those questions for you. So again, no spoilers. Tomorrow after his lesson, please don't post questions about it on Twitter yet. Those of you that are responding to me on Twitter did a great job yesterday keeping this stuff kind of quiet, so that way people had a chance to go through it. So if you do have questions about today's answers, feel free to reach out to me. And then Greg will get you set up with 2 brand new full-length questions tomorrow to practice. And then you guys are getting close to being ready. So again, if there's any topical areas you need to pick up, browse through our playlist. We've got lots of good stuff on there, Greg and myself, lots of good topical review. If you're just finding this YouTube page for the first time, feel free to scroll back. We've got weeks worth of review. Pretty good stuff. We've got live demos, live illustrations, practice problems, and it's all geared towards the 2020 exam. So it's all worth your time. So thanks for watching. Again, my name is Joshua Beck. I have enjoyed working with you guys. I'll be back at the very end of the week. Greg's taking over for Wednesday and Thursday to administer his practice questions. So feel free to reach out to me on Twitter with questions, and also feel free to check in tomorrow for one more practice exam. All right, appreciate you guys. Have a good afternoon.